Okay, hello everybody. Today we're going to be talking about Delanoid paths. So, I'm sure many of you are already familiar with something called a lattice path. It's a very common math competition problem where you need to count the number of paths in the grid of Z2 from 0, 0 to Mn using only steps 1, 0 or 0, 1. I'm going to denote these as R and U. So to get to the point Mn, we'll need a total of M Rs and N Us. And so in the case of a lattice path, there's simply M plus N choose M such paths. However, with the Delanoid path, we add a new rule, which allows us to take a diagonal step in the direction 1, 1. And the question is, how many such paths are there from 0, 0 to Mn given this new rule? Well, we're going to denote the number of such paths as dmn, and our goal is to find an expression for the number of such paths. To do this, we'll break up these paths into different cases, and we're going to group the paths by the number of diagonal steps in the path, and we'll call this J. And so now, if we can solve the general problem where we have J diagonal steps, then we can simply take our expression, sum over all possible values of J, and since each case is non-overlapping, we'll get the final answer. So how would we do that? Well, we know that taking J diagonal steps advances us on the x-axis, and on the y-axis it advances us plus J in either direction. So we can think about taking J diagonal steps. If we took them first, it would take us from 0, 0 to JJ. And now the question is how many R's and U's would take us from JJ to Mn. And this is just simply M minus J R's and N minus J U's, which simplifies to M plus N minus 2J. So this is the number of R's and U's, and J is the number of D's. So in total, we have a sequence of M plus N minus J R's, U's, and D's. All right. So how do we count these sequences? Well, we actually know that the number of R's and the number of D's has to be M. Why is this? Well, because we're going from an x-coordinate of 0 at the start, and we're landing up at a point with an x-coordinate of M. So the only way to move horizontally is with the R's and the D's. So, given that fact, the way we can count the number of such sequences of R's, U's, and D's is by first choosing some M of the original M plus N minus J slots to be our R's and D's. And when we do this, we implicitly select the remaining elements to be U's. And then once we've chosen the slots for the R's and the D's, we know that they're exactly J D's. So we select, of the M slots, we select J of them to be D's, and then implicitly the rest are R's. So we found our answer. dmn is simply the sum from all possible values of J of M plus N minus J, choose M, times M choose J. So that's how you solve the problem. And now let me give you an exercise to think about. And this is a non-trivial exercise, so do not feel bad if you cannot get this, but just something to think about if you're bored. We define a lattice ball of radius m in Zn to be the set of all points P in Zn such that the taxicab distance from the origin to P is at most m. So the most simple case, when m and n are both 2, we're in the plane Z2, and our taxicab distance is at most 2, so our lattice ball looks something like this. And we define Lmn to simply be the size of this set. So how would we, the question, the exercise, is how do we compute Lmn? And once you think you have a formula for that, the follow-up exercise, so that's part A. Part B is to prove that Lmn is actually equal to Dmn, the number of Delaunay paths. And this fact might be pretty astonishing. It was to me at first, but I think it's pretty cool that this works out. A hint for part A is to think of each point in the lattice ball as an n-dimensional vector with the property that x1 plus up to xn is at most n, the absolute values. And see if you can solve for the number of these solutions, the number of solutions for this vector x. To try and count those solutions, see if you can do a similar partitioning to what we did with the Delaunay paths. And once you've come up with that formula, I think this isn't really a hint, this is pretty obvious for how to prove this fact, but you're going to need to come up with it by ejection. And if you get stuck, you can always try to look at the book Combinatorial Mathematics by Doug West. So I hope you enjoyed this video, and I hope you guys think about these problems. Thank you.